Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this semicircle that is inside quarter circle AOB. In the second question, we'll find out the area of this green shape that is inside rectangle ABCD. So we'll start with the first question. So in the drawing we have a quarter circle, AOB is a quarter circle, and we know that AO equals to 5 units in its length. That is to say, the radius of this quarter circle is 5 units, and inside this quarter circle we have this semicircle, and our mission is to find out the area of this semicircle. So in the first step, we will define the center of this semicircle. This point is point C. We will define the touching point of the quarter circle with the semicircle, this point, as point E. We will define the second touching point of the semicircle with this quarter circle, this point, as point F. Likewise, we will define the point of tendency of tangent AO with this semicircle, this point, as point G. And finally, we will define the point of tendency of tangent OB with this semicircle, this point is point H. And we know that the radius of the quarter circle equals to 5 units in its length, and we will define the radius of this semicircle as x. Therefore, CE equals to CF. They are both the radii of this semicircle. This is equals to x according to our definition. In the next step, we will join point C and H together by a straight line. CH is the radius of this semicircle. According to our definition, the radius of this semicircle equals to x, therefore CH equals to x. Likewise, we will join point C and G together by a straight line. So CG is the radius of this semicircle, that equals to x according to our definition. So here we have the radius CG of this semicircle that is drawn to point G, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius GC. If AO is perpendicular to GC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CH of this semicircle is drawn to point H, that is the point of tendency of tangent OB with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius HC. If OB is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. By doing this construction, we get the quadrilateral CGOH. Inside quadrilateral CGOH, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule. Then the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral CGHO, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at a rectangle, if not a square. So we relate to this quadrilateral CGOH as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CGOH, side CG must be equal to the opposite side OH. But CG is X, therefore OH must be also equal to X. Likewise, according to the same rule, in the same rectangle CGOH, side GO must be equal to the opposite side CH. But CH equals to X, and therefore GO must be also equal to X. So actually found out that quadrilateral CGOH is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this square is equal to X. Okay? So in the next step, we will join points O and C together by a straight line. Point O is the center of the quarter circle. So we have in the drawing AOB is a quarter circle, and from the center of the quarter circle we draw line segment OC that bisect chord FE. Again, line segment OC bisect chord FE. Why line segment OC bisect chord FE? Because of the fact that CF equals to CE. It means that line segment OC bisect chord FE into 2 halves. Each half equals to X. CF equals to X and CE also equals to X. So, in conclusion, you can say that the line segment OC that exists from the center of the quarter circle, that is to say from point O, bisects chord FE. And whenever you have a line segment that is drawn from the center of the circle and it bisects a chord, you can implement here rule 7. So I repeat quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of a circle bisects a chord, then the line segment will be also perpendicular to that chord. So in the drawing we have a circle. Point O is the center of the circle. From the center of the circle, that is to say from point O, we have line segment OM that bisects chord AB. Why? Because we know that MA equals to MB, and therefore line segment OM bisects chord AB. And because of the fact that line segment OM bisects chord AB, line segment OM also perpendicular to chord AB. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 7. So I can actually implement rule 7 in our drawing. Why? Because in our drawing we have line segment OC that exists from the center of the quarter circle, that is to say from point O, line segment OC bisect chord FE. That is to say, it divides it into two halves. The first half is CF and the second half is CE. And CF equals to CE. So according to rule 7, because of the fact that line segment OC bisect chord FE, line segment OC will be also perpendicular to FE. If OC is perpendicular to FE, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. Okay? So in the next step, we will join points O and E together by straight line. What is the definition of line segment OE? Line segment OE starts from point O, that is the center of the quarter circle, and ends at point E, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of this quarter circle, and we know that the radius of the quarter circle equals to 5 units in its length, and therefore OE equals to 5 units. In the next step, I will copy the right triangle CHO in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle CHO. CHO is also an isosceles triangle. Why? Because we know that CH equals to HO. So CHO is the right and isosceles triangle. So according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is abbreviation for Pythagoras theorem. Side CH equals to x, side HO also equals to x, and CO, the hypotenuse CO is the missing side. So actually, this is the right and associated triangle, triangle CHO. According to the Pythagoras theorem, in this right triangle CHO, CO squared, that is the square of the hypotenuse, must be equal to CH squared plus HC squared. CO squared equals to CH squared plus HO squared. So I write it down. So actually, CO squared, that is the square of the hypotenuse, equals to CH squared plus HO squared. CO is the missing side, so we will leave it as it is. So CO squared equals to CH squared. CH equals to x, therefore CH squared equals to x squared plus HO squared. HO equals to x, therefore HO squared equals to x squared. So in total, CO squared equals to x squared plus x squared, that is 2x squared. So we found out that CO squared equals to 2x squared. Here we take a root out of this equation, and finally we get that the missing hypotenuse CO is equals to the square root of 2 times x. So we found out that CO equals to the square root of 2 times x units in its length. So in the next step, I'll copy the right green triangle, triangle OCE in a new page, and we'll implement the Pythagoras theorem on this green right triangle OCE. here by PT is a version for Pythagoras theorem. The hypotenuse OE equals to 5 units in its length. So here, this is the right green triangle, triangle OCE. This is the green right triangle OCE that they copied from the original drawing. According to the Pythagoras theorem, in this right triangle OCE, OE square, that is the square of the hypotenuse, equals to CE square plus CO square. And again, in the right triangle OCE, according to the Pythagoras theorem, OE square equals to CE square plus CO square. OE is 5, therefore OE square is 5 square, that is 25. And it is equals to CE square. CE is x, therefore CE square is x square plus CO square. CO is square root of 2 times x, therefore CO square is square root of 2 times x squared, that is actually 2x squared. So in total we should find out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So we should find out that 25 equals to 3x squared. Here we divide this equation by 3. And finally we get that x squared equals to 25 over 3. So we found out that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. The area of any semicircle is the area of the circle over 2. The area of a circle with radius of x is pi x squared. And therefore the area of the semicircle will be equal to pi x squared over 2. So the area of the semicircle equals to pi x squared over 2. So it is pi over 2 times x squared. And x squared is 25 over 3. So we substitute x squared in this equation by 25 over 3. And we get that in total the area of the semicircle equals to 25 pi over 2 times 3, that is 6. So it is 25 pi over 6 square units. Or in terms of numbers, it is equals to 13.09 square units. Repeat again. We actually found out that the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, the area of this semicircle equals to 13.09 square units. So we finished with the first question. In the next step, I present to you the second question, and we answer on the second question. So in the drawing, we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle, we have this semicircle, and we have also this quarter circle. And our mission is to find out the area of this green shape. So, first of all, we will define the center of this semicircle. This point is point E. ABCD is a rectangle. ABCD is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB equals to the opposite side CD. But AB is 5, therefore CD must be also equal to 5 units in its length. So CD equals to 5 units in its length. So I write it down. BC is one side of rectangle ABCD, but BC is also the radius of the quarter circle. I repeat again, BC is also the radius of this quarter circle. We will define the radius of the quarter circle as x. Therefore, BC equals to x according to our definition. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. So we found out that the diameter of this semicircle, that is AD, equals to x units. If the diameter is x, then the radius of this semicircle must be equal to x over 2. So the radius AE of this semicircle equals to x over 2. And the radius ED is also equals to x over 2 units in its length. We know that ABCD is a rectangle, and all the angles inside the rectangle are right angles. Therefore, this is angle ADC, that is a right angle. So, in the drawing, we have an external lunge between the quarter circle and the semicircle. That is to say, they touch each other externally at this point. This is their touching point. We will define this point that is their touching point as point S. So, in the drawing, we have an external lunge between the semicircle and the quarter circle. And whenever you have an external lunge between two circles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching point. So in the drawing we have two circles. Those two circles have an external lunge between them. That is to say, they touch each other externally at this point, point P. In addition, we know that the center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects the centers together is, of course, the straight line OM. And according to rule 10, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass for their touching point, that is point P. Or OPM is one straight line. Again, according to this rule 10, OPM is one straight line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, we have an external lunge between this semicircle and this quarter circle. That is to say, they touch each other externally at this point, point S. Now we can implement here rule 10. We know that the center of this quarter circle is here at point C. The center of this semicircle is here at point E. And the straight line that connects their centers together is of course the straight line EC. And according to rule 10, the straight line EC must pass through point S, that is their touching point. Again, the straight line EC must pass through point S, that is their touching point. Or ESC is one straight line. Again, ESC is one straight line according to rule 10. So we join points E and C together by straight line, and you know that the straight line EC must pass through point S, that is their touching point, or ESC is one straight line. So you can see here that the straight line EC that connects the centers together, again the straight line EC that connects their centers together passes through point S, that is their touching point. ESC is one straight line. Because of the fact that ESC is one straight line, it means that EC will be equal to ES plus SC. So I write it down. Again, EC equals to ES plus SC. EC equals to ES plus SC. So EC equals to ES. What is the definition of line segment ES? Line segment ES starts from point E, that is the center of the semicircle, and then at point S, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, ES is the radius of this semicircle. That is equals to x over 2 units according to what we have already found out. So ES is the radius of this semicircle. That is equals to x over 2. What is the definition of line segment SC? Line segment SC starts from point C, that is the center of the quarter circle, and ends at point S, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, SC is the radius of this quarter circle. That is equal to x according to our definition. So SC equals to x. So in total, we actually found out that EC equals to ES, that is x over 2, plus SC, that is x. So in total, EC equals to x over 2 plus x. X over 2 plus x equals to 1.5x, or 3 over 2x. In conclusion, we found out that EC equals to 3 over 2x units in its length. In the next step, I'll copy the right triangle EDC in a new page, and we'll implement the Pythagoras theorem on this right triangle, triangle EDC. ED equals to x over 2 units in its length. We have already found out that DC equals to 5 units in its length. And finally, the hypotenuse EC equals to 3 over 2 x units in its length. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle EDC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle EDC, EC square equals to ED square plus DC square. So I write it down. EC square, it is the square of the hypotenuse, equals to ED square plus DC squared. EC equals to 3 over 2x, therefore EC squared equals to 3 over 2x squared. 3 over 2x squared equals to 9 over 4x squared, and it is equals to ED squared. ED is x over 2, therefore ED squared is x over 2 squared, that is x squared over 4 plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So actually found out that 9 quarters times x squared equals to 1 quarter x squared plus 25. Here we subtract minus x squared, we subtract x squared over 4 for this equation, and we get that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared, and it is equals to 25. 8 over 4 is 2, so this expression equals to 2x squared. So 2x squared equals to 25. Here we divide this equation by 2, and finally we get that x squared equals to 25 over 2. X squared equals to 25 over 2. Here we take a root out of this equation, and finally we get that x equals to the square root of 25 over 2. The square root of 25 is 5, so it is 5 over square root of 2. So in conclusion, we should find out that x equals to 5 over 2 square units. Actually, x is the radius of this quarter circle. Found out the radius of the quarter circle, x equals to 5 over 2 square units. 5 over square root of 2 units, and x squared equals to 25 over 2. Our mission is to find out the area of this green shape. So what is the area of the green shape? So actually, from the drawing, it is very easy to see that the area of the green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Repeat again, I actually found out that the area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So the area of the green shape equals to the area of rectangle ABCD. What is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. The length is AB, that is 5, the width is BC, that is x, so in total the area of rectangle ABCD equals to 5x. So the area of rectangle ABCD equals to 5x minus the area of the semicircle. What is the area of the semicircle? The area of any semicircle equals to the area of the circle over 2. The radius of this semicircle is x over 2. So the area of any semicircle equals to the area of the circle, that is pi times the radius of the circle squared, and therefore the area of the semicircle will be equal to pi times the radius of the circle divided by 2 minus the area of the quarter circle. The area of any quarter circle equals to the area of the circle over 4, and the area of the circle is pi times the radius of the circle squared over 4. So if we found out that in total the area of the green shape equals to the area of the rectangle ABC, that is 5x, minus the area of the semicircle, that is pi, and the radius of the semicircle is x over 2. So it is pi times x over 2 squared divided by 2, minus the area of the quarter circle. The radius of this quarter circle is x. And therefore, the area of the quarter circle will be equal to pi times x squared over 4. So the area of the green shape equals to 5x. Here we have pi times x over 2 squared is pi times x squared over 4 divided by 2 minus pi x squared over 4. So here we have 5x minus pi x squared over 8, and here we have minus pi x squared over 4. Here we multiply both the numerator and the denominator of this expression by 2 in order to have a common factor with this expression. So after we multiply both the numerator and the denominator of this expression by 2, it will be equal to minus 2 pi x squared divided by 8. So the area of the green shape in total equals to 5x. And we have here minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total we shall find out that the area of the green shape equals to 5x minus 3 pi x squared over 8. But we have already found out that x equals to 5 over the square root of 2 units and x squared equals to 25 over 2. Therefore we can substitute x in this expression by 5 over square root of 2 and x squared by 25 over 2. We'll do it now and we get that the area of the green shape in total equals to 5 times x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So we substitute x squared by 25 over 2. So in total we shall find out the area of the green shape equals to, here we have 5x, 5 times 5 is 25, so it is 25 over square root of 2 minus, here we have 3 pi times 25 is 75 pi, and the denominator we have 8 times 2, that is 16. So in total we shall find out that the area of the green shape is equals to 25 over square root of 2 minus 75 pi over 16 square units. Or in terms of numbers, it is equals to 2.95 square units. And that is the answer to the question. I repeat again, we actually found out that the area of this green shape equals to either 25 over square root of 2 minus 75 pi over 16 square units, or in terms of numbers, it is equals to 2.95 square units. Okay, so in the next step, I will summarize the lecture. We start with the first question, of course. In the first question, we found out the area of this semicircle that is inside this quarter circle A or B. So in the drawing we have quarter circle AOB. We know that AO equals to 5 units in its length. That is to say the radius of this quarter circle is 5. Inside this quarter circle we have this semicircle. And our mission is to find out the area of this semicircle. So in the first step we define the center of this semicircle, this point as point C. We define the touching point of the quarter circle with this semicircle, this point as point E. Likewise, we define the touching point of the quarter circle with this semicircle, this point as point F. We define the point of tendency of tangent AO with this semicircle, this point as point G. And finally, we define the point of tendency of tangent BO with this semicircle, this point as point H. In the next step, we join point C and H together by a straight line. CH is the radius of this semicircle. Why? Because line segment CH starts from point C, that is the center of the semicircle, and H at point H, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, CH is the radius of this semicircle. We define the radius of this semicircle as x. Therefore, CH equals to x. Likewise, we join point C and G together by a straight line. CG is, of course, the radius of this semicircle. That is equals to x according to our definition. So here we have the radius CG of this semicircle is equals to x. The radius CG is drawn to point G, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius GC. If AO is perpendicular to GC, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CH of this semicircle. The radius CH is drawn to point H, that is the point of tendency of tangent OB with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius HC. If BO is perpendicular to HC, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we created a quadrilateral CGOH. Inside this quadrilateral CGOH, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral CGOH we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral CGOH as a rectangle because it has 4 right angles. So inside quadrilateral CGOH, that is 4 right angles. So we relate to this quadrilateral CGOH as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CGOH, side CG must be equal to the opposite side OH. But CG is x, therefore OH must be also equal to x. Likewise, according to the same rule, in the same rectangle CGOH, side CH must be equal to the opposite side GO. But CH equals to x, therefore GO must be also equal to x. So actually found out that quadrilateral CGOH is not a rectangle, but a square, right, because of the fact that all of its sides are equal to each other. Each side of this square is equal to x. In the next step, we join points O and C together by a straight line. Point O is the center of the quarter circle. So from the center of the quarter circle, we have here line segment OC that bisect chord EF. Again, from the center of this quarter circle, that is to say from point O, we have here line segment OC that bisect chord EF. And therefore, we can implement here rule 7. Repeat quickly on rule 7. According to rule 7, if a line segment is drawn from the center of the circle, bisect the chord, then the line segment will be also perpendicular to the chord. So in the drawing we have a circle, the center of this circle is 0.0. And we have 9/7 OM bisect chord AB. Again, 9/7 OM bisect chord AB. That is to say, MA equals to MB. And because of the fact that 9/7 OM bisect chord AB, 9/7 OM will be also perpendicular to chord AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 7. So whenever you draw a line segment from the center of the circle that bisects the chord, then it will be also perpendicular to that chord. Here we have 9/7 OM that bisect chord AB, and therefore 9/7 OM is also perpendicular to AB. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, we have point O is the center of this quarter circle. So from the center of the quarter circle, that is to say from point O, we have line segment OC that bisects chord EF. That is to say, CE equals to CF. And for that reason, 9/7 OC, according to rule 7, also will be perpendicular to chord EF. If OC is perpendicular to EF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 7. In the next step, we implemented the Pythagoras theorem on the right triangle CHO. So I copied the right triangle CHO in a new page and implemented the Pythagoras theorem on this right triangle, triangle CHO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle CHO that I call it from the original drawing. CH equals to HO equals to X. Therefore, this triangle CHO is also an associated triangle. So in the right triangle CHO, according to the Pythagoras theorem, CO square equals to CH square plus HO square. Again, CO square equals to CH square plus HO square. CO is the missing side, so we will leave it as it is. So CO square equals to CH square. CH is X, therefore CH square is X square plus HO square. HO is also X, therefore HO square is X square. So in total, CO square equals to X square plus X square, that is 2X square. So CO square equals to 2X square. We took a root out of this equation and finally found out that CO, the missing hypotenuse CO, is equals to the square root of 2 times X units in its length. So we found out that this is the missing side CO that equals to the square root of 2 times X units in its length. In the next step, we join points O and E together by a straight line. What is the definition of line segment OE? Line segment OE starts from point O, that is the center of the quarter circle, and that's at point E, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of this quarter circle, that is equals to 5 units in its length, because we know that the radius of this quarter circle, according to what is given us in the question, equals to 5, because AO equals to 5, and AO is the radius. So OE is the radius of the quarter circle, that is equals to 5 units in its length. In the next step, I copied the right green triangle OCE in a new page, and we implemented the Pythagoras theorem on this green right triangle OCE. So actually, this is the right green triangle OCE that I copied from the original drawing. CE is the radius of the semicircle, that is equals to X. We just right now found out that CO equals to the square root of 2 times X, and EO is the radius of the quarter circle, that is equals to 5. So according to the Pythagoras theorem, in this right triangle CEO, EO square, that is the square of the hypotenuse, must be equal to CE square plus CO square. Repeat again. EO square, that is the square of the hypotenuse, must be equal to CE square plus CO square. Again, EO is 5. It is the radius of the quarter circle, that is equals to 5. Therefore, EO square is 5 square, that is 25. And it is equals to CE square. CE is X, therefore CE square is X square. CE square is X square plus CO square. CO is square root of 2 times X, therefore CO square is square root of 2 times X squared, that is actually 2X squared. 0 squared is 2x squared. So in total, 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So in conclusion, I actually found out that 25 equals to 3x squared. Here we divided this equation by 3 and finally found out that x squared equals to 25 over 3. Okay? X squared equals to 25 over 3. Our mission is to find out the area of this semicircle. And the area of the semicircle equals to the area of the circle over 2. The area of the circle is pi x squared, and therefore the area of the semicircle is pi x squared over 2, because x is the radius. Because again, the area of the semicircle equals to pi x squared over 2. So it is pi over 2 times x squared, and x squared is 25 over 3. Therefore, we substitute x squared in this equation by 25 over 3. In total, we actually found out that the area of the semicircle equals to pi over 2 times x squared, and x squared is 25 over 3. So in total, the area of the semicircle equals to 25 pi over 2 times 3, that is 6. So in total, the area of the semicircle equals to either 25 pi over 6 square units, or in terms of numbers, it is equals to 13.09 square units. I repeat again, we actually found out that the area of this semicircle equals to either 25 pi over 6 square units, so in terms of numbers, it is equals to 13.09 square units. We finished with the first question. In the next step, I actually presented to you the second question. We solve the second question. Our mission in the second question is to find out the area of this green shape. So in the drawing, we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD, we have this semicircle and this quarter circle. The semicircle touches the quarter circle at this point. Point S is their touching point. Again, our mission is to find out the area of this green shape. So first of all, we know that all the angles inside the rectangle are right angles. Therefore, this is angle ADC, that is a right angle. In addition, we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5 units in its length. We defined the radius of this quarter circle, that is to say BC, that is the radius of this quarter circle, as x. So the radius of this quarter circle equals to x according to our definition. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. AD is one side of rectangle ABCD, but AD is also the diameter of this semicircle. So the diameter of this semicircle, AD equals to x. If the diameter AD is x, the radius must be equal to x over 2. So the radius AE of this semicircle equals to x over 2, and the radius ED also equals to x over 2 units in its length. So ED equals to x over 2 units. So here we have an external length between this semicircle and this quarter circle. That is to say, they touch each other externally, this point S. And whenever you have an external length between two circles or semicircles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing we have two circles. Those two circles touch each other externally at this point, point P. Therefore they have an external between them at point P. The center of this circle is there at point O. The center of this circle is there at point M. And the straight line that connects the centers together is of course the straight line OM. According to this rule 10, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through their touching point, that is point P. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external between this semicircle and this quarter circle, that is to say they touch each other externally at point S. The center of this semicircle is there at point E. The center of this quarter circle is there at point C. And the straight line that connects their centers together is of course the straight line EC. And according to rule 10, the straight line EC must pass through point S, that is their touching point. Again, the straight line EC must pass through point S, that is their touching point. Or ESC is one straight line. Again, according to rule 10, ESC is one straight line. If ESC is one straight line, it means that EC will be equal to ES plus SC. Again, EC equals to ES plus SC. Repeat again, EC equals to ES plus SC. ES is the radius of this semicircle, that is equals to x over 2. And SC is the radius of this quarter circle, that is equal to x, according to our definition. So in total, EC equals to EC equals to ES, that is x over 2, plus SC, that is x. So in total, EC equals to x over 2 plus x, that is 3 over 2x. Again, we actually found out that the length of right segment EC is 3 over 2x. In the next step, I copied the right triangle EDC in a new page and implemented the Pythagoras theorem on this right triangle, triangle EDC. So actually, this is the right triangle EDC that I copied from the original drawing. We just right now found out that the hypotenuse EC of this right triangle EDC equals to 3 over 2x units in its length. ED is the radius of the semicircle, that is x over 2, and DC equals to 5 units in its length. According to the Pythagoras theorem, in this right triangle EDC, EC square equals to ED square plus DC square. Again, EC square equals to ED square plus DC square. EC is 3 over 2x, therefore EC square is 3 over 2x squared. That is actually 9 over 4x squared, and it is equals to ED square. ED is x over 2, therefore ED square is x over 2 squared. That is x squared over 4 plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So here we subtracted x squared over 4 from this equation, and finally found out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared. So 8 quarters x squared equals to 25. 8 over 4 is 2, so in total this expression equals to 2x squared, and 2x squared equals to 25. Here we divided this equation by 2, and finally found out that x squared equals to 25 over 2. Here we took a root out of this equation, and finally found out that x equals to the square root of 25, that is 5, over square root of 2. Again, x equals to 5 over square root of 2 units in its length, and x squared equals to 25 over 2. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. I repeat again, the area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. What is the area of rectangle ABCD? The area of this rectangle ABCD equals to the length of the rectangle times the width. The length is 5, the width is x, therefore in total the area of rectangle ABCD equals to 5x. And the area of rectangle ABCD equals to 5x. Minus the area of this semicircle. The area of this semicircle equals to the area of the circle over 2. The area of the circle equals to pi times the radius of the circle squared over 2. The radius is x over 2. And therefore the radius squared is x over 2 squared. So in total, the area of the semicircle equals to pi times x over 2 squared divided by 2. Repeat again. The area of the semicircle equals to pi times the radius of the circle over 2. And the area of the quarter circle equals to the area of the circle over 4. The radius of the circle is x. So the area of the quarter circle equals to pi times the radius of the circle divided pi times the radius of the circle squared over 4. So the area of the green shape in total equals to 5x, and the radius of this semicircle is x over 2, therefore the radius squared is x over 2 squared divided by 2. So in total, the area of the semicircle equals to pi times x over 2 squared divided by 2 minus the area of this semicircle. The radius of this semicircle is x, therefore the area of the semicircle will be equal to pi x squared over 4. And again, the area of the semicircle equals to pi x squared over 2. To pi x squared over 4. So in total, the area of the green shape equals to 5x. Here we open the brackets. X over 2 squared is x squared over 4. So in total, this expression equals to pi x squared over 4 divided by 2. Minus the area of the quarter circle, that is pi x squared over 4. So here we have pi x squared over 2 times 4, that is 8. So in total we have this expression equals to pi x squared over 8. So here we multiply this both the numerator and the denominator of this expression by 2 in order to have a common factor with this expression. So after we multiply both the numerator and the denominator of this expression by 2, this expression will be equal to pi x squared over 2 times 4, that is 8. So in total this expression will be equal to 2 pi minus 2 pi x squared over 8. Minus 2 pi x squared over 8. So in total the area of the green shape equals to 5x minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total the area of the green shape equals to 5x minus 3 pi x squared over 8. But we have already found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2. Therefore, we can substitute x squared by 25 here by 25 over 2 and x by 5 over square root of 2. We did it, and we should find out the area of the green shape in total equals to 5x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total, we actually found out that the area of the green shape equals to, here we have 5 times 5, that is 25. So in total, this expression equals to 25 over square root of 2 minus 3 pi times 25, that is 75 pi over 2 times 2 is 16. So this expression in total equals to 75 pi over 16. So in total, we actually found out that the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. In terms of numbers, the area of this green shape equals to 2.95 square units. I repeat again, the area of this green shape equals to either 25 over square root of 2 minus 25 pi over 16 square units, or in terms of numbers, the area of this green shape equals to 2.95 square units. Okay, thank you very much.